If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The invisible sculptor of the cosmos. Magnetism is a silent force, invisible to the naked eye yet powerful enough to sculpt the cosmos. Across the vastness of space, this phenomenon wields its influence, governing the motion of particles, shaping celestial bodies, and guiding the evolution of galaxies. But how does it achieve all this? To understand magnetism's role in the universe, we must first appreciate its foundation, an interaction between charged particles that creates magnetic fields capable of stretching across light years. Unlike gravity, which always pulls, magnetic forces can both attract and repel, offering a dynamic interplay that allows for complex and often beautiful cosmic phenomena. Magnetism is not confined to specific regions of the universe. It's a ubiquitous force, present in stars, planets, interstellar gas, and even in the smallest subatomic particles. Its reach extends from the swirling clouds of dust where stars are born to the event horizons of black holes, making it a cornerstone of cosmic evolution. At the heart of magnetism lies motion, specifically the motion of charged particles. When these particles move, they generate magnetic fields, which in turn influence the behavior of other particles nearby. This feedback loop creates a dance that defines much of what we observe in the universe. However, unlike gravity, which scientists have extensively modeled, magnetism in space remains a frontier with many unanswered questions. It's a puzzle that invites astronomers, physicists, and curious minds alike to unravel its secrets. When we observe the universe, we often focus on its visible aspects: stars, galaxies, and glowing nebulae. But magnetism works behind the scenes, orchestrating the movement and interaction of these elements. In many ways, it is the unseen architect of cosmic structures. For example, the swirling arms of spiral galaxies owe their shape partly to magnetic forces that guide the flow of interstellar gas. These fields are not static. They evolve with time, responding to the changing dynamics of the galaxies they inhabit. Magnetism's influence begins at the smallest scales, within individual atoms, and extends to the vast scales of intergalactic space. This scale invariance allows it to play a role in phenomena as diverse as the auroras dancing above Earth's poles and the colossal jets of plasma shooting out from active galactic nuclei. Its ability to operate across such a broad spectrum of scales makes it a universal force, one that transcends boundaries and categories. One of the most compelling aspects of magnetism is its ability to act as a sculptor. Consider the formation of stars. Dense clouds of gas and dust collapse under gravity, but magnetic fields thread through these clouds, resisting collapse and influencing how material flows. They guide the gas into specific shapes and regulate the rate at which stars form, acting as both a brake and a channel for the birth of new stars. Without these magnetic threads, star formation would likely look very different, possibly more chaotic and less efficient. But magnetism's role doesn't end with the birth of stars. It also shapes their lives and deaths. As stars rotate, they generate magnetic fields that can create sunspots, flares, and other magnetic phenomena. These fields interact with stellar winds, creating magnetic bubbles around stars that influence nearby planetary systems. Even in death, stars leave magnetic fingerprints. The remnants of massive stars, like neutron stars and magnetars, are some of the most magnetically intense objects in the universe, capable of warping space-time and generating bursts of high-energy radiation. Magnetism also bridges the gap between the cosmic and the terrestrial. Earth's magnetic field, for instance, protects us from the sun's solar wind, a stream of charged particles that could strip away our atmosphere and make life on our planet impossible. This magnetic shield creates the auroras we see near the poles, but it also serves as a reminder of how integral magnetism is to the existence of life itself. In galaxies, magnetism doesn't just shape stars and planets. It also governs the behavior of cosmic rays, high-energy particles that traverse the universe. These particles are guided by magnetic fields, which act as cosmic highways, directing them and sometimes even accelerating them to near-light speeds. By studying these interactions, scientists gain insight into the processes occurring in the farthest reaches of the universe. On a grander scale, magnetic fields may have played a critical role in the early universe just after the Big Bang. Some theories suggest that primordial magnetic fields emerged during the universe's infancy, influencing the distribution of matter and energy. If these fields existed, they would have left subtle imprints on the cosmic microwave background, the faint afterglow of the Big Bang. Studying these imprints could unlock clues about the universe's origins and its ultimate fate. Yet, for all its importance, magnetism remains one of the least understood forces in astrophysics. Unlike gravity, which can be described using relatively straightforward equations, magnetism in space operates within the framework of magnetohydrodynamics, a complex and often unpredictable interplay of magnetic fields and fluid dynamics. This complexity makes it both a challenge and a frontier for scientific discovery. Magnetism's pervasive influence also raises questions about its origins. Where do these magnetic fields come from? How do they maintain themselves over cosmic timescales? Some fields are generated locally by the movement of charged particles, while others may be relics of ancient cosmic events. Scientists are using advanced simulations and observations to unravel these mysteries, but much remains unknown. As we continue to explore the universe, magnetism serves as a reminder of the unseen forces that shape our reality. Its influence is subtle yet profound, guiding the cosmos in ways that often go unnoticed but are no less essential. Every aurora, every star, every galaxy owes part of its existence to this invisible sculptor, making magnetism one of the most intriguing forces of the universe. The invisible sculptor of the cosmos. Magnetism is a silent force, invisible to the naked eye yet powerful enough to sculpt the cosmos. Across the vastness of space, this phenomenon wields its influence, governing the motion of particles, shaping celestial bodies, and guiding the evolution of galaxies. But how does it achieve all this? To understand magnetism's role in the universe, we must first appreciate its foundation, an interaction between charged particles that creates magnetic fields capable of stretching across light years. Unlike gravity, which always pulls, magnetic forces can both attract and repel, offering a dynamic interplay that allows for complex and often beautiful cosmic phenomena. Magnetism is not confined to specific regions of the universe. It's a ubiquitous force, present in stars, planets, interstellar gas, and even in the smallest subatomic particles. Its reach extends from the swirling clouds of dust where stars are born to the event horizons of black holes, making it a cornerstone of cosmic evolution. At the heart of magnetism lies motion, specifically the motion of charged particles. When these particles move, they generate magnetic fields, which in turn influence the behavior of other particles nearby. This feedback loop creates a dance that defines much of what we observe in the universe. However, unlike gravity, which scientists have extensively modeled, magnetism in space remains a frontier with many unanswered questions. It's a puzzle that invites astronomers, physicists, and curious minds alike to unravel its secrets. When we observe the universe, we often focus on its visible aspects: stars, galaxies, and glowing nebulae. But magnetism works behind the scenes, orchestrating the movement and interaction of these elements. In many ways, it is the unseen architect of cosmic structures. For example, the swirling arms of spiral galaxies owe their shape partly to magnetic forces that guide the flow of interstellar gas. These fields are not static. They evolve with time, responding to the changing dynamics of the galaxies they inhabit. Magnetism's influence begins at the smallest scales, within individual atoms, and extends to the vast scales of intergalactic space. This scale invariance allows it to play a role in phenomena as diverse as the auroras dancing above Earth's poles and the colossal jets of plasma shooting out from active galactic nuclei. Its ability to operate across such a broad spectrum of scales makes it a universal force, one that transcends boundaries and categories. One of the most compelling aspects of magnetism is its ability to act as a sculptor. Consider the formation of stars. Dense clouds of gas and dust collapse under gravity, but magnetic fields thread through these clouds, resisting collapse and influencing how material flows. They guide the gas into specific shapes and regulate the rate at which stars form. acting as both a break and a channel for the birth of new stars. Without these magnetic threads, star formation would likely look very different, possibly more chaotic and less efficient. But magnetism's role doesn't end with the birth of stars. It also shapes their lives and deaths. As stars rotate, they generate magnetic fields that can create sunspots, flares, and other magnetic phenomena. These fields interact with stellar winds, creating magnetic bubbles around stars that influence nearby planetary systems. Even in death, stars leave magnetic fingerprints. The remnants of massive stars like neutron stars and magnetars are some of the most magnetically intense objects in the universe, capable of warping space-time and generating bursts of high-energy radiation. Magnetism also bridges the gap between the cosmic and the terrestrial. Earth's magnetic field, for instance, protects us from the sun's solar wind, a stream of charged particles that could strip away our atmosphere and make life on our planet impossible. This magnetic shield creates the auroras we see near the poles, but it also serves as a reminder of how integral magnetism is to the existence of life itself. In galaxies, magnetism doesn't just shape stars and planets. It also governs the behavior of cosmic rays, high-energy particles that traverse the universe. These particles are guided by magnetic fields, which act as cosmic highways, directing them and sometimes even accelerating them to near-light speeds. By studying these interactions, scientists gain insight into the processes occurring in the farthest reaches of the universe. On a grander scale, magnetic fields may have played a critical role in the early universe, just after the Big Bang. Some theories suggest that primordial magnetic fields emerged during the universe's infancy, influencing the distribution of matter and energy. If these fields existed, they would have left subtle imprints on the cosmic microwave background, the faint afterglow of the Big Bang. Studying these imprints could unlock clues about the universe's origins and its ultimate fate. Yet, for all its importance, magnetism remains one of the least understood forces in astrophysics. Unlike gravity, which can be described using relatively straightforward equations, magnetism in space operates within the framework of magnetohydrodynamics, a complex and often unpredictable interplay of magnetic fields and fluid dynamics. This complexity makes it both a challenge and a frontier for scientific discovery. Magnetism's pervasive influence also raises questions about its origins. Where do these magnetic fields come from? How do they maintain themselves over cosmic timescales? Some fields are generated locally by the movement of charged particles, while others may be relics of ancient cosmic events. Scientists are using advanced simulations and observations to unravel these mysteries, but much remains unknown. As we continue to explore the universe, magnetism serves as a reminder of the unseen forces that shape our reality. Its influence is subtle yet profound, guiding the cosmos in ways that often go unnoticed, but are no less essential. Every aurora, every star, every galaxy owes part of its existence to this invisible sculptor, making magnetism one of the most intriguing forces of the universe. Magnetic fields and star birth. The birth of stars is one of the most fundamental processes in the universe, a cycle that transforms clouds of gas and dust into luminous celestial bodies. While gravity is often hailed as the primary driver of star formation, magnetism plays an equally vital, though less understood role. Magnetic fields act as cosmic architects, guiding the collapse of interstellar clouds, regulating the flow of matter, and even determining the characteristics of the stars that emerge. Imagine a cold, dark molecular cloud floating in the depths of space, a vast reservoir of gas and dust that holds the potential for stellar creation. These clouds are crisscrossed by magnetic field lines, invisible threads that exert a subtle, yet powerful influence. As gravity begins to pull the cloud inward, these magnetic fields resist the collapse, providing a counterforce that shapes how the cloud contracts. This interplay between gravity and magnetism sets the stage for the formation of stars. Without magnetic fields, the collapse of molecular clouds would likely be chaotic, resulting in rapid and uncontrolled star formation. Instead, magnetism imposes order, acting like a scaffolding that channels the flow of gas into specific regions. These regions, often dense filaments within the cloud, become the cradles where stars are born. Observations of star-forming regions, such as the Orion Nebula, reveal these filaments as intricate networks, highlighting the role of magnetic fields in organizing the raw material of stars. But magnetic fields do more than just guide the collapse. They also regulate it. As gas falls inward, it carries with it magnetic field lines, a process known as flux freezing. This intensifies the local magnetic field, creating a feedback mechanism that slows the rate of collapse. By moderating the flow of matter, magnetism ensures that star formation proceeds at a controlled pace, preventing the entire cloud from collapsing into a single massive star. Magnetism also influences the angular momentum of collapsing clouds. As gas spirals inward, it begins to spin faster, much like an ice skater pulling in their arms. This rotation would ordinarily prevent further collapse, but magnetic fields act as a brake, redistributing angular momentum and allowing the cloud to contract further. This braking mechanism is essential for the formation of protostars, the dense cores that eventually ignite into full-fledged stars. Protostars are not isolated entities. They form within larger systems that often include disks of gas and dust. These protoplanetary disks are the birthplaces of planets, but their formation and evolution are closely tied to magnetism. Magnetic fields thread through these disks, driving complex processes that influence their structure and dynamics. For example, magnetized winds can carry away excess angular momentum, enabling the disk to shrink and feed material onto the growing star. In some cases, magnetic fields become so intense that they create spectacular jets of material shooting out from the poles of the protostar. These jets, which can stretch for light years, are a hallmark of star formation and serve as a mechanism for shedding angular momentum. They also provide astronomers with a visual representation of the magnetic forces at work, offering clues about the hidden dynamics within the star-forming region. Magnetism's role in star birth extends to the chemical composition of the resulting stars. As magnetic fields guide the flow of gas, they influence the mixing and distribution of elements within the molecular cloud. This mixing determines the abundance of elements like carbon, oxygen, and nitrogen in the protostar, which in turn affects its future evolution and the potential for planet formation in its vicinity. One of the most intriguing aspects of magnetic fields in star formation is their ability to shape not just individual stars, but entire star clusters. Molecular clouds often give birth to groups of stars, and magnetic fields help determine the spacing and size of these stellar nurseries. By influencing how gas fragments within the cloud, magnetism ensures a balance between solitary stars and tightly packed clusters. The study of magnetic fields in star-forming regions is a challenging endeavor, as these fields are difficult to detect directly. Astronomers rely on indirect methods, such as observing the polarization of light, to infer the presence and orientation of magnetic fields. These observations have revealed that magnetic fields are often aligned with the filaments in molecular clouds, underscoring their role as organizers of star-forming material. While magnetism is a crucial player in star formation, it is not the only force at work. Turbulence, radiation, and gravitational interactions all contribute to the process, creating a complex interplay of forces. Yet, magnetism serves as a unifying thread, linking these elements and providing a framework for understanding the intricate dynamics of star birth. Recent advances in technology, such as the use of radio telescopes and computer simulations, have allowed scientists to probe magnetic fields in unprecedented detail. Instruments like the Atacama Large Millimeter/Submillimeter Array ALMA have captured stunning images of star-forming regions, revealing the fine structure of magnetic fields and their influence on the surrounding gas and dust. These observations are helping astronomers piece together the puzzle of how stars form and evolve. Magnetism's influence doesn't end when a star is born. Newly formed stars often retain strong magnetic fields, which shape their subsequent evolution and interactions with their environment. For instance, magnetic activity on young stars can drive powerful stellar winds that clear away the surrounding gas, influencing the development of planetary systems. These winds can also inject energy into the interstellar medium, contributing to the next cycle of star formation. The story of star birth is one of transformation, where diffuse clouds of gas and dust coalesce into brilliant points of light that illuminate the universe. Magnetism, though unseen, plays a central role in this story, guiding the process with a delicate balance of forces. It sculpts the raw material of the cosmos into the stars that populate galaxies, making it an essential force in the cosmic cycle of creation. Magnetars, the magnetic monsters. In the vast expanse of the universe, magnetars stand as enigmatic beacons of extreme magnetism and untamed energy. These rare and extraordinary objects, a type of neutron star, possess magnetic fields so powerful that they defy conventional understanding. Magnetars are not only cosmic marvels, but also laboratories of physics, where the most extreme conditions in the universe test the limits of our knowledge. What makes them so unique, and what can they teach us about the fundamental forces that govern the cosmos? Magnetars are born from the catastrophic deaths of massive stars. When a star with a mass several times that of the Sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a supernova explosion. The core of the star is compressed into an incredibly dense object known as a neutron star, a celestial body with the mass of the Sun packed into a sphere no larger than a city. In rare cases, this collapse gives rise to a magnetar, a neutron star with a magnetic field 1 trillion times stronger than Earth's. To put this into perspective, the magnetic field of a typical magnetar is so intense that it could strip atoms of their electrons from thousands of kilometers away. If one were to come within half the distance to the moon, its magnetic forces would erase the data on every credit card on Earth. These magnetic fields are the strongest in the known universe, making magnetars unique cosmic laboratories for studying the interplay of matter, energy, and magnetism under extreme conditions. Magnetars are not just magnetically intense, they are also extraordinarily dynamic. They emit bursts of high-energy radiation, including X-rays and gamma rays, that can outshine entire galaxies for brief periods. These bursts, known as soft gamma repeaters and giant flares, are thought to be triggered by sudden shifts in the magnetar's magnetic field. Imagine a planet-sized earthquake, but instead of tectonic plates shifting, the crust of the neutron star cracks and releases an enormous amount of energy. The crust of a magnetar is no ordinary material. Composed of a dense lattice of atomic nuclei, it is subjected to pressures and temperatures far beyond anything found on Earth. The intense magnetic field deforms the crust, creating immense stress that can cause it to fracture. When this happens, magnetic energy is rapidly converted into heat and light, producing the dramatic outbursts that make magnetars so fascinating. But where do magnetars get their magnetic power? Scientists believe that their fields are amplified during the star's collapse. As the core of the dying star contracts, the magnetic field lines are compressed, intensifying the field through a process known as flux conservation. Additionally, the rapid rotation of the newborn neutron star, often spinning hundreds of times per second, generates electric currents that further amplify the magnetic field. Over time, however, magnetars lose their rotational energy and spin down. This slowdown is much faster than that of typical neutron stars, a clue that the magnetar's magnetic field is breaking its rotation. As the magnetic field dissipates, the magnetar transitions into a quieter state, emitting less radiation and becoming harder to detect. These dormant magnetars, or magnetar fossils, may populate the galaxy in greater numbers than we realize, hidden among the myriad neutron stars. Despite their rarity, magnetars play a significant role in the broader cosmic ecosystem. The energy they release during flares can influence their surroundings, heating nearby gas and triggering the formation of new stars. Their intense magnetic fields also accelerate particles to near-light speeds, creating cosmic rays that travel across the universe and impact other systems. In this way, magnetars serve as both destroyers and creators, reshaping their environment with each outburst. The study of magnetars has far-reaching implications for our understanding of physics. Their extreme conditions offer a natural laboratory for testing theories about the behavior of matter under immense pressure and magnetic stress. For instance, scientists are exploring how magnetars challenge our models of quantum mechanics, nuclear physics, and general relativity. These investigations may even provide insights into phenomena beyond astrophysics, such as the properties of exotic particles and the unification of fundamental forces. One of the most intriguing aspects of magnetars is their potential connection to fast radio bursts, FRBs, mysterious and powerful flashes of radio waves that originate from distant galaxies. Recent observations suggest that at least some FRBs may be produced by magnetars during their energetic outbursts. If true, this connection could help unravel the mystery of FRBs and shed light on the life cycles of magnetars. Magnetars are also candidates for the source of high-energy neutrinos, elusive particles that rarely interact with matter. Detecting neutrinos from magnetar flares would provide valuable information about the processes occurring deep within these objects, offering a glimpse into regions that are otherwise inaccessible to observation. Such discoveries could revolutionize our understanding of particle physics and astrophysics alike. The search for magnetars continues, driven by advanced observatories equipped to detect their faint emissions. Instruments like NASA's NICER, Neutron Star Interior Composition Explorer, and the Chandra X-ray Observatory are at the forefront of this research, providing high-resolution data that helps scientists map the magnetic landscapes of these enigmatic stars. Future missions may uncover more magnetars, revealing new details about their formation, evolution, and impact on the cosmos. Despite decades of study, magnetars remain a puzzle with many unanswered questions. Why do some neutron stars become magnetars while others do not? What determines the strength and lifetime of their magnetic fields? How do their magnetic outbursts propagate through space? And what effects do they have on distant systems? These questions drive ongoing research, promising new insights into one of the most extreme and captivating phenomena in the universe. Magnetars are more than just curiosities. They are windows into the fundamental workings of the cosmos. Their immense magnetic power challenges our understanding of nature, pushing the boundaries of what is possible. As we continue to explore these magnetic monsters, we are reminded of the universe's capacity for both mystery and wonder, a testament to the boundless complexity of the stars above. Galactic magnetism. Galaxies are more than sprawling collections of stars, gas, and dark matter. They are also crisscrossed by vast, invisible magnetic fields that shape their structure and evolution. These fields, though weak compared to those of stars or planets, span thousands of light years and influence processes ranging from star formation to the behavior of cosmic rays. Galactic magnetism is one of the universe's hidden forces, subtle yet pervasive, leaving its mark on every corner of the cosmos. At first glance, the magnetic fields of galaxies might seem insignificant. After all, their strength is often measured in microgauss, 1,000,000 times weaker than Earth's magnetic field. However, their sheer scale makes them a significant force. Imagine a magnetic field that stretches across an entire spiral galaxy, threading through its arms and influencing the motion of gas and dust within. These fields are like scaffolding, providing structure and guidance to the galactic material. Spiral galaxies, such as our Milky Way, are particularly notable for their organized magnetic fields. Observations reveal that these fields often align with the spiral arms, tracing the pathways of interstellar gas and dust. This alignment is not coincidental. It results from a complex interaction between the galaxy's rotation, the movement of charged particles, and the dynamics of the interstellar medium. The process by which these fields are generated and maintained is known as the dynamo effect, a mechanism that converts kinetic energy into magnetic energy. The dynamo effect relies on the rotation of the galaxy and the motion of charged particles within it. As gas and plasma move through the galaxy, their motion generates electric currents, which in turn produce magnetic fields. Over time, these fields are amplified and organized, creating the large-scale structures we observe today. The details of this process are still being studied, but it is clear that the dynamo effect is a key driver of galactic magnetism. Galactic magnetic fields are not confined to the visible disk of the galaxy. They extend far into the halo, the diffuse region surrounding the galaxy. In some cases, these fields connect neighboring galaxies, forming bridges of magnetized plasma that span vast distances. These intergalactic magnetic fields may play a role in the evolution of galaxy clusters, influencing the flow of gas and the formation of new stars. They also act as cosmic highways for charged particles, guiding the paths of cosmic rays as they traverse the universe. Cosmic rays, high-energy particles that originate from sources like supernovae and active galactic nuclei, interact with galactic magnetic fields in fascinating ways. As these particles travel through space, they are deflected and scattered by magnetic fields, creating a diffuse glow of radio waves that astronomers can observe. This interaction not only helps map the structure of magnetic fields, but also provides clues about the origins and acceleration of cosmic rays. In addition to shaping the motion of cosmic rays, galactic magnetic fields influence the behavior of interstellar gas. Magnetic pressure, a force exerted by the field, can counteract the pull of gravity, regulating the collapse of gas clouds and the formation of stars. This balance is crucial for maintaining the steady pace of star formation in galaxies, preventing bursts of activity that would rapidly deplete the available gas. The influence of magnetic fields extends to the large-scale structure of the universe. Observations of galaxy clusters, the largest gravitationally bound structures in the cosmos, reveal that their hot gas is threaded with magnetic fields. These fields, though weak, are thought to stabilize the gas and prevent it from collapsing under its own gravity. They may also play a role in the formation of the cosmic web, the vast network of filaments and voids that connects galaxies across the universe. One of the most intriguing aspects of galactic magnetism is its origin. Where do these magnetic fields come from, and how have they evolved over billions of years? Some theories suggest that they are primordial, arising from the universe's earliest moments. Tiny magnetic fields generated during the Big Bang may have been amplified over time by processes like the dynamo effect, growing into the large-scale fields we see today. Alternatively, magnetic fields could have been seeded by the first stars and galaxies, spreading outward as these objects evolved. The study of galactic magnetism is a relatively young field, but advancements in technology are opening new windows into this hidden force. Instruments like the Square Kilometre Array, SK, a next-generation radio telescope, promise to map magnetic fields in unprecedented detail, revealing their structure and dynamics across vast distances. Polarized light, a key tool for detecting magnetic fields, is helping astronomers trace the alignment of fields within galaxies and beyond. Galactic magnetism also has implications for understanding dark matter, the mysterious substance that makes up most of the universe's mass. Magnetic fields interact with visible matter, but they may also be influenced by dark matter. By studying the distribution and behavior of magnetic fields, scientists hope to uncover clues about the nature of dark matter and its role in shaping galaxies. Despite the progress being made, many questions about galactic magnetism remain unanswered. How do magnetic fields interact with other forces, such as gravity and turbulence? What role do they play in the evolution of galaxies over cosmic timescales? And how do they connect to the larger magnetic structure of the universe? These questions drive ongoing research, pushing the boundaries of what we know about the cosmos. Galactic magnetism is a reminder of the universe's complexity, a force that operates on scales both small and immense, subtle yet impactful. It threads through galaxies like an unseen web, shaping their structure and guiding their evolution. As scientists continue to unravel its mysteries, they are uncovering a force that is not just a backdrop to cosmic events, but a central player in the story of the universe. Black holes and magnetic chaos. Black holes, the enigmatic regions of space-time where gravity reigns supreme, are often associated with their immense gravitational pull. However, these cosmic titans also harbor powerful magnetic fields that play a crucial role in shaping their environments. From the chaotic dynamics of accretion disks to the colossal jets of plasma that pierce intergalactic space, magnetism is an essential component of the black hole phenomenon. How does this invisible force interact with one of the universe's most extreme objects? At the heart of a black hole's magnetic chaos lies its accretion disk, a swirling maelstrom of gas, dust, and plasma that spirals toward the event horizon. As matter falls inward, it becomes heated to millions of degrees, emitting intense radiation. This process is far from orderly. The turbulent motion of charged particles generates electric currents, which in turn produce magnetic fields. These fields can grow to immense strengths, driving the violent activity that characterizes black holes. Magnetic fields within accretion disks are not static. They evolve in response to the chaotic motion of the surrounding material. One key mechanism that amplifies these fields is the magnetorotational instability, MRI, a process that arises when differential rotation in the disk stretches and twists magnetic field lines. MRI generates turbulence, which both enhances the magnetic field and facilitates the transport of angular momentum. This allows matter to move inward toward the black hole while ejecting excess energy outward. One of the most spectacular manifestations of black hole magnetism is the formation of relativistic jets, beams of plasma that are propelled outward at nearly the speed of light. These jets, which can extend for thousands of light years, are among the most energetic phenomena in the universe. They are powered by a combination of rotational energy from the black hole and magnetic fields within the accretion disk. The exact mechanism behind their formation is still an active area of research, but scientists believe that magnetic fields play a central role in converting rotational energy into the kinetic energy of the jets. The interaction between a black hole's spin and its magnetic field is described by the Blanford's-Najac process, a theoretical model that explains how energy is extracted from a rotating black hole. In this process, magnetic field lines anchored in the accretion disk twist around the black hole, creating a dynamo effect that drives the outflow of energy. This mechanism not only powers the jets but also influences the evolution of the black hole itself, gradually slowing its rotation over time. Magnetic fields around black holes are also responsible for shaping their immediate environments. In some cases, these fields act as barriers, preventing matter from falling directly into the black hole. Instead, material accumulates in the accretion disk, where it undergoes complex interactions before crossing the event horizon. This magnetic gatekeeping can influence the rate at which black holes grow, affecting their role in the evolution of galaxies. The chaotic interplay between magnetism and gravity near black holes creates extreme conditions that push the boundaries of physics. Temperatures soar, matter is compressed to densities rivaling atomic nuclei, and particles are accelerated to near-light speeds. These environments provide a natural laboratory for studying phenomena like relativistic plasmas, magnetic reconnection, and the behavior of matter under intense gravitational and magnetic forces. Magnetic reconnection, in particular, is a key process near black holes. This occurs when magnetic field lines break and reconnect, releasing vast amounts of energy. In the vicinity of a black hole, reconnection events can accelerate particles to ultra-high energies, producing flares of radiation that are detectable across vast cosmic distances. These flares, often observed in X-rays and gamma rays, offer clues about the magnetic dynamics at play. The influence of black hole magnetism extends far beyond their immediate vicinity. Relativistic jets powered by magnetic fields inject energy into the surrounding galaxy, heating interstellar gas and regulating star formation. In galaxy clusters, these jets can create cavities in the hot gas that pervades the cluster, shaping its structure and dynamics. By redistributing energy on such large scales, black holes and their magnetic fields act as cosmic architects, influencing the evolution of galaxies and clusters over billions of years. Observing magnetic fields near black holes is a formidable challenge, but advancements in technology are beginning to yield insights. The Event Horizon Telescope, EHT, which captured the first image of a black hole shadow, has also provided data on the polarization of light near the event horizon. Polarization carries information about magnetic fields, allowing scientists to map their structure and dynamics. These observations are helping to refine theoretical models and deepen our understanding of black hole magnetism. Black hole magnetism is not confined to supermassive black holes at the centers of galaxies. It also plays a role in smaller, stellar mass black holes. These black holes, which form from the collapse of massive stars, often accrete matter from companion stars. The interaction between their magnetic fields and the accreting material produces phenomena like X-ray binaries and microquasars, scaled-down versions of the activity seen in supermassive black holes. The study of magnetic fields near black holes is still in its infancy, but it holds the promise of answering some of the most profound questions in astrophysics. How do magnetic fields influence the growth of black holes and the formation of jets? What role do they play in the creation of high-energy cosmic rays and neutrinos? And how do they interact with the fabric of space-time near the event horizon? These questions drive ongoing research, pushing the limits of our knowledge about the universe's most extreme objects. Magnetism and black holes are a paradoxical pairing. One is a force of order, threading through the cosmos with precision, while the other is a force of destruction, consuming everything in its path. Yet, their interaction creates some of the most dynamic and fascinating phenomena in the universe. Together, they weave a story of chaos and creation, a testament to the complexity and beauty of the cosmos. Magnetic fields of exoplanets. In the hunt for life beyond Earth, magnetic fields may be one of the most critical factors determining a planet's habitability. While much of the attention in exoplanet studies has focused on their atmospheres, sizes, and distances from their stars, the presence or absence of a magnetic field could profoundly influence a planet's ability to support life. What role do magnetic fields play in the environments of these distant worlds? And how are scientists uncovering their secrets? Magnetic fields act as planetary shields, protecting atmospheres from being stripped away by stellar winds and cosmic radiation. On Earth, the magnetosphere deflects the solar wind, a stream of charged particles emitted by the sun. Without this protective barrier, the solar wind would erode our atmosphere, leaving the planet barren and uninhabitable. This scenario is thought to have occurred on Mars, which lost its magnetic field billions of years ago. The subsequent loss of its atmosphere transformed it from a potentially habitable world into the dry, cold desert we see today. Exoplanets orbiting other stars are exposed to similar, and often more extreme, conditions. Many stars, particularly red dwarfs, are highly active, emitting intense radiation and frequent stellar flares. Planets in close proximity to these stars, even if they reside in the habitable zone, face a constant barrage of charged particles. In such environments, a strong magnetic field could be the difference between retaining an atmosphere and losing it to space. Detecting magnetic fields on exoplanets, however, is a formidable challenge. Unlike stars, which emit copious amounts of light, exoplanets are dim and distant, making direct observations of their magnetic properties nearly impossible. Scientists must rely on indirect methods to infer their presence. One promising approach involves observing the interactions between exoplanets and their host stars. When a planet with a magnetic field orbits close to its star, it can generate detectable signals, such as radio emissions or variations in stellar activity, through magnetic interactions. Radio emissions are particularly intriguing because they could provide a direct measurement of an exoplanet's magnetic field strength. On Earth, similar emissions, known as auroral radio bursts, are generated when charged particles from the solar wind interact with the planet's magnetosphere. By detecting similar signals from exoplanets, astronomers hope to map their magnetic environments and assess their potential habitability. Another method involves studying exoplanet atmospheres during transits when the planet passes in front of its star. If a planet has a magnetic field, it may create a magnetosphere that influences the way its atmosphere interacts with stellar radiation. Observing these interactions can provide clues about the presence and strength of magnetic fields. The discovery of magnetic fields around exoplanets would have profound implications for understanding their potential to support life. For one, magnetic fields help retain atmospheres, which are essential for regulating surface temperatures and enabling liquid water. They also protect the surface from harmful cosmic radiation, which can damage DNA and other biological molecules. Without a magnetic field, even planets with Earth-like conditions could be rendered uninhabitable by relentless radiation. Magnetic fields may also influence the geological activity of exoplanets. On Earth, the movement of molten iron in the core generates our magnetic field through the dynamo effect. This same process drives plate tectonics, which regulates the carbon cycle and maintains a stable climate over geological timescales. If exoplanets lack magnetic fields, they may also lack the tectonic activity needed to sustain long-term habitability. In recent years, scientists have identified several exoplanets where magnetic fields might be present. For example, observations of the hot Jupiter WASP 12b suggest that it interacts magnetically with its host star, producing enhanced stellar activity. Similarly, the Earth-sized planet Proxima Centauri b, located in the habitable zone of the nearest star to the Sun, may possess a magnetic field strong enough to shield it from its star's intense radiation. If confirmed, these findings would mark a significant step forward in the search for habitable worlds. Magnetic fields are not only relevant for habitability, but also for understanding the diversity of planetary systems. Gas giants like Jupiter and Saturn have immense magnetic fields that shape their moon's environments. For instance, Jupiter's magnetosphere influences the volcanic activity on its moon Io and creates powerful auroras on Ganymede. Similar interactions may occur in exoplanetary systems, with magnetic fields shaping the dynamics of moons, rings, and plasma environments. Studying magnetic fields on exoplanets also offers a window into their interiors. The presence of a magnetic field suggests a liquid, electrically conducting core, which provides clues about the planet's composition and thermal evolution. By combining magnetic data with other observations, such as mass and radius, scientists can build a more complete picture of an exoplanet's structure and history. Despite the challenges, advances in technology are bringing the detection of exoplanet magnetic fields closer to reality. Upcoming radio telescopes, like the Square Kilometer Array, (SK), will have the sensitivity to detect faint radio emissions from distant planets, potentially revolutionizing our understanding of their magnetic properties. Meanwhile, missions like the James Webb Space Telescope, JWST, and the European Space Agency's Ariel mission aim to study exoplanet atmospheres in greater detail, providing indirect evidence of magnetic fields through their interactions with stellar radiation. As our understanding of exoplanetary magnetism grows, so does the possibility of finding worlds that not only resemble Earth in size and composition, but also in their ability to sustain life. Magnetic fields, often overlooked in the search for habitable planets, may prove to be one of the most critical factors in determining whether a planet can harbor life. By unlocking the secrets of magnetic fields, scientists are expanding the boundaries of what we know about the universe and bringing us closer to answering one of humanity's most profound questions. Are we alone? Cosmic rays and magnetic highways. Cosmic rays, high-energy particles that streak through space at nearly the speed of light, are among the most enigmatic travelers in the universe. Composed primarily of protons, along with heavier nuclei and electrons, these particles originate from powerful cosmic events such as supernova explosions, active galactic nuclei, and colliding neutron stars. However, their journey through the universe is far from a straight line. Magnetic fields, stretching across galaxies and intergalactic space, serve as highways and barriers, guiding and scattering cosmic rays across the cosmos. But what do these magnetic interactions reveal about the nature of the universe? The story of cosmic rays begins in the violent environments where they are born. Supernovae, the explosive deaths of massive stars, are thought to be one of the primary sources of cosmic rays within our galaxy. During these cataclysmic events, shock waves accelerate particles to immense speeds, hurling them into space. Similarly, the powerful jets of active galactic nuclei, driven by supermassive black holes, can propel particles to energies billions of times greater than those achieved by human-made particle accelerators. Once released, cosmic rays embark on a journey through a universe filled with magnetic fields. These fields, generated by the motion of charged particles, are found in stars, planets, and galaxies, as well as in the tenuous plasma of intergalactic space. Unlike light, which travels in straight lines, cosmic rays are charged particles and thus are deflected by magnetic fields. Their paths become twisted and tangled, creating a journey that is as much a map of magnetic influences as it is a record of their origins. In our galaxy, the Milky Way, magnetic fields are particularly influential. The galactic magnetic field, structured along the spiral arms, acts as a vast network of highways, guiding cosmic rays along certain paths while scattering them in others. This interaction creates a diffuse glow of gamma rays, produced when cosmic rays collide with interstellar gas and dust. Observing this gamma ray glow helps scientists trace the structure of the galactic magnetic field and understand how cosmic rays are distributed. Cosmic rays don't remain confined to galaxies. They also traverse the intergalactic medium, the vast expanses of space between galaxies, where magnetic fields are much weaker, but still significant. These intergalactic magnetic fields are thought to be remnants of the early universe, amplified and stretched by the formation of large-scale cosmic structures. As cosmic rays travel through these fields, their paths are influenced by the magnetic texture of the universe, revealing clues about the history and evolution of cosmic magnetism. One of the most intriguing questions in astrophysics is how cosmic rays achieve their incredible energies. Some cosmic rays, known as ultra-high-energy cosmic rays, carry more energy than a baseball traveling at 90 miles per hour, yet their origins remain a mystery. Scientists suspect that these particles are accelerated in extreme environments, such as the jets of active galactic nuclei or the turbulent regions of galaxy clusters, where magnetic fields play a crucial role in boosting particle energies. Magnetic fields also act as barriers, protecting planets from the harmful effects of cosmic rays. On Earth, the magnetosphere deflects most cosmic rays, shielding the surface from their potentially damaging radiation. However, some cosmic rays penetrate the atmosphere, where they interact with molecules to produce secondary particles, including muons and neutrinos. These interactions create a cascade of particles that scientists study to understand the properties of cosmic rays and their origins. The effects of cosmic rays extend beyond Earth. In space, astronauts and spacecraft are exposed to higher levels of cosmic radiation, which poses significant risks to human health and electronic systems. Understanding the interactions between cosmic rays and magnetic fields is crucial for designing effective shielding for future space missions, particularly those venturing beyond the protective magnetosphere of Earth. Cosmic rays also influence the chemistry and climate of planetary atmospheres. On Earth, they play a role in the formation of cloud condensation nuclei, tiny particles around which water vapor condenses to form clouds. This connection suggests that cosmic rays may have a subtle but significant impact on weather and climate, linking the behavior of the cosmos to the conditions on our planet. The study of cosmic rays and magnetic fields has also opened new windows into particle physics. When cosmic rays collide with particles in Earth's atmosphere, they produce showers of secondary particles, some of which are extremely rare or short-lived. These interactions provide a natural laboratory for studying fundamental particles and forces, complementing experiments conducted in human-made accelerators like the Large Hadron Collider. Detecting cosmic rays is a challenging task, requiring specialized instruments both on the ground and in space. Ground-based observatories, such as the Pierre Auger Observatory in Argentina, detect the showers of particles created when cosmic rays strike the atmosphere. Space-based detectors, like the Alpha Magnetic Spectrometer on the International Space Station, directly capture cosmic rays as they travel through space. These instruments are helping scientists unravel the mysteries of cosmic rays, from their origins to their interactions with magnetic fields. One of the most exciting recent developments in cosmic ray research is the detection of high-energy neutrinos, ghostly particles that are produced alongside cosmic rays in energetic astrophysical processes. Unlike cosmic rays, neutrinos are electrically neutral and are not deflected by magnetic fields, allowing them to travel in straight lines from their sources. By studying neutrinos, scientists can complement their understanding of cosmic rays and identify the locations of their most powerful accelerators. Cosmic rays and magnetic fields are intertwined in a cosmic dance that shapes the universe on both small and large scales. From the behavior of individual particles to the structure of galaxies and beyond, their interactions provide a window into the fundamental forces that govern the cosmos. As scientists continue to study these phenomena, they are uncovering new layers of complexity and gaining deeper insights into the workings of the universe. The Sun's magnetic personality. The Sun, a blazing sphere of plasma that powers life on Earth, is far more than a simple ball of light and heat. Beneath its radiant exterior lies a churning magnetic heart that shapes not only its own behavior, but also the dynamics of the entire solar system. The Sun's magnetic field is the driving force behind solar flares, coronal mass ejections, and the solar wind, phenomena collectively known as solar activity. But how does this magnetic dynamo work, and how does it influence our cosmic neighborhood? The Sun's magnetism arises from its dynamic interior, where a complex interplay of heat, rotation, and plasma movement generates its magnetic field. This process, known as the solar dynamo, occurs in the convection zone, a layer beneath the Sun's surface where hot plasma rises and cooler plasma sinks. The movement of electrically charged particles in this turbulent zone creates electric currents, which in turn produce magnetic fields. The sun's rotation twists and amplifies these fields, creating a dynamic and ever-changing magnetic system. The sun's magnetic field is not uniform. It is highly structured, with regions of concentrated magnetic activity that manifest as sunspots on the solar surface. Sunspots are cooler, darker areas where magnetic fields are particularly intense, often bundling together in pairs or groups with opposite polarities. These regions serve as the focal points for solar activity, where powerful magnetic forces drive spectacular events such as solar flares and coronal mass ejections. Solar flares are sudden bursts of energy caused by the release of magnetic stress in the sun's atmosphere. They occur when magnetic field lines twist, snap, and reconnect, releasing energy in the form of light, heat, and high-energy particles. These particles, including electrons and protons, are hurled into space, sometimes reaching Earth and affecting our planet's magnetic environment. Large flares can disrupt satellite communications, cause power grid failures, and produce beautiful auroras near the poles. Coronal mass ejections, CMEs, on the other hand, are massive expulsions of plasma and magnetic fields from the sun's corona. Unlike flares, which release energy locally, CMEs involve the ejection of billions of tons of solar material into space. These clouds of charged particles travel outward at millions of kilometers per hour, carrying with them the sun's magnetic field. When CMEs collide with Earth's magnetosphere, they can trigger geomagnetic storms, which may disrupt power systems, navigation, and even pipelines. The solar wind, a continuous stream of charged particles flowing from the sun, is another manifestation of its magnetic activity. The solar wind originates in the corona, the sun's outer atmosphere, where magnetic fields guide the escape of plasma into space. This wind shapes the heliosphere, a vast bubble of solar influence that extends far beyond the orbit of Pluto. Within this bubble, the solar wind interacts with the magnetic fields of planets, shaping their magnetospheres and influencing space weather. The sun's magnetic activity is not constant. It follows an approximately 11-year cycle of waxing and waning intensity. At the peak of this cycle, known as solar maximum, the sun's magnetic field becomes highly complex, with numerous sunspots and frequent flares and CMEs. During solar minimum, the field becomes simpler, with fewer sunspots and reduced activity. This cycle is driven by the solar dynamo, which periodically reverses the polarity of the sun's magnetic field. The effects of the solar cycle extend far beyond the sun itself. Variations in solar activity influence Earth's upper atmosphere, affecting satellite orbits, radio communications, and navigation systems. Solar activity also modulates the intensity of cosmic rays reaching Earth, as the solar wind acts as a shield that deflects these high-energy particles. During periods of high solar activity, the increased solar wind reduces the flux of cosmic rays, while during low activity, more cosmic rays penetrate the heliosphere. The sun's magnetic influence is not limited to Earth. It extends to every planet and object within the heliosphere, shaping the magnetic environments of worlds both near and far. For instance, Mercury, with its weak magnetic field, experiences direct interaction with the solar wind, leading to the stripping of its thin atmosphere. Jupiter, on the other hand, has a massive magnetosphere that captures solar wind particles and creates intense radiation belts. Understanding the sun's magnetic behavior is critical for predicting space weather, which can have significant impacts on modern technology. Spacecraft, satellites, power grids, and communication networks are all vulnerable to the effects of solar storms. To mitigate these risks, scientists use data from solar observatories, such as NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar Orbiter, to monitor and model the sun's activity in real time. The study of the sun's magnetic field also provides insights into the broader workings of stars. The processes that generate the sun's magnetic field are thought to occur in stars of all types, shaping their activity and evolution. By studying the sun, scientists gain a deeper understanding of stellar magnetism and its role in the universe. Despite centuries of observation, the sun's magnetic field remains a source of mystery. How does the solar dynamo operate in such a dynamic and turbulent environment? What triggers the most powerful solar flares and CMEs? And how does the sun's magnetic field interact with the interstellar medium beyond the heliosphere? These questions drive ongoing research, pushing the boundaries of solar physics and our understanding of the cosmos. The sun's magnetic personality is a reminder of the intricate forces at work in the universe. It shapes the solar system, influences the conditions on Earth, and connects us to the broader story of stellar evolution. As scientists continue to explore the sun's magnetic mysteries, they are uncovering the secrets of a force that is as essential to life as it is to the workings of the cosmos. Magnetospheres and planetary protection. Across the solar system and beyond, planetary magnetospheres serve as invisible shields, safeguarding their worlds from the relentless onslaught of charged particles streaming through space. These protective bubbles, generated by magnetic fields, not only influence planetary climates and surface conditions, but also play a critical role in maintaining atmospheres and enabling the possibility of life. How do magnetospheres form? And what can they tell us about the past, present, and future of planets? Magnetospheres are regions where a planet's magnetic field dominates the behavior of charged particles. They arise from the interaction between a planet's magnetic field and the solar wind, a stream of plasma continuously emitted by the sun. As the solar wind encounters the planet, the magnetic field deflects it, creating a protective barrier. This interaction forms a teardrop-shaped structure, with the side facing the sun compressed and the opposite side stretching into a long tail. The existence and strength of a magnetosphere depend on several factors, including the planet's size, rotation rate, and internal structure. On Earth, the magnetosphere is powered by the dynamo effect, a process driven by the movement of molten iron in the planet's outer core. This motion generates electric currents, which in turn produce the magnetic field. The rapid rotation of Earth enhances this dynamo, creating a strong and dynamic magnetosphere. One of the most critical roles of Earth's magnetosphere is protecting its atmosphere. Without this magnetic shield, the solar wind would strip away atmospheric particles, as has happened on Mars. Billions of years ago, Mars is thought to have had a thick atmosphere and surface water, conditions potentially conducive to life. However, the loss of its global magnetic field left the planet exposed to the solar wind, which gradually eroded its atmosphere and transformed it into the barren world we see today. Venus, another planet without a significant magnetic field, offers a similar cautionary tale. Despite being similar in size and composition to Earth, Venus lacks a magnetosphere, leaving its dense atmosphere vulnerable to direct interaction with the solar wind. This interaction creates a weak induced magnetosphere, driven by the ionized layer of Venus's atmosphere, but it is insufficient to fully protect the planet. In contrast, Jupiter's magnetosphere dwarfs all others in the solar system. Generated by the rapid rotation of the planet's metallic hydrogen interior, Jupiter's magnetic field creates a magnetosphere that extends millions of kilometers into space. This immense structure captures high-energy particles and produces intense radiation belts, which are lethal to spacecraft and any potential life forms. Jupiter's magnetosphere also influences its moons, particularly Io, which experiences intense volcanic activity, partly driven by its interaction with the planet's magnetic field. Saturn, Uranus, and Neptune also possess strong magnetospheres, each with unique characteristics. Saturn's magnetosphere, for instance, interacts with its ring system, while Uranus and Neptune have highly tilted magnetic axes, creating unusual and asymmetric magnetospheres. These differences provide valuable insights into the diversity of planetary magnetic environments and their effects on surrounding space. Beyond the solar system, exoplanets may also possess magnetospheres that influence their habitability. For planets orbiting close to their stars, such as hot Jupiters and super-Earths, strong magnetic fields could protect their atmospheres from being stripped away by stellar winds and flares. Conversely, the absence of a magnetic field might render even Earth-like planets inhospitable, as their atmospheres would be eroded over time. The study of magnetospheres extends beyond planetary protection. Magnetospheric interactions produce stunning phenomena, such as auroras, which occur when charged particles from the solar wind are funneled along magnetic field lines and collide with atmospheric gases. On Earth, These collisions create shimmering displays of green, red, and purple lights near the poles. Similar auroras have been observed on Jupiter, Saturn, and even Uranus, each with its unique characteristics. Magnetospheres also play a role in shaping space weather, the dynamic conditions in space driven by the sun's activity. During solar storms, when the sun emits intense bursts of radiation and charged particles, magnetospheres act as the first line of defense. On Earth, the magnetosphere deflects most of these particles, but during particularly strong storms, it can be overwhelmed, leading to geomagnetic storms that disrupt satellites, power grids, and communication systems. Despite their importance, magnetospheres are not invulnerable. Earth's magnetic field, for example, is known to undergo periodic reversals, where the magnetic poles switch places. These geomagnetic reversals, which occur over thousands to millions of years, temporarily weaken the magnetosphere, making the planet more vulnerable to cosmic and solar radiation. While the exact causes of these reversals are still under investigation, they highlight the dynamic nature of planetary magnetism. Studying magnetospheres requires advanced instruments and missions. Spacecraft like NASA's Magnetospheric Multiscale (MMS) mission and the European Space Agency's Cluster mission provide detailed measurements of Earth's magnetosphere, while missions to other planets, such as Juno at Jupiter and Cassini at Saturn, have revealed the unique properties of their magnetic environments. Future missions aim to explore the magnetospheres of Uranus and Neptune, as well as potential magnetospheres around exoplanets. Understanding magnetospheres is not just a scientific endeavor. It has practical implications for space exploration. As humans venture deeper into space, magnetospheres will play a critical role in shielding astronauts and equipment from harmful radiation. Learning to navigate and utilize these magnetic environments will be essential for establishing sustainable human presence beyond Earth. Magnetospheres are a testament to the interconnectedness of planetary systems, linking internal processes with external influences in a dynamic balance. They protect, shape, and sometimes transform the worlds they encompass, making them one of the most fascinating and vital aspects of planetary science. As we continue to explore our solar system and beyond, magnetospheres remain a cornerstone of our understanding of planetary habitability and the complex forces that govern the cosmos. Magnetic breaks, slowing stellar spins. Stars are born spinning rapidly, their youthful rotations fueled by the collapse of immense clouds of gas and dust. Yet, as stars age, their rotations slow down, often to a fraction of their original speed. This deceleration, known as magnetic braking, is one of the most critical processes in stellar evolution, shaping the life cycles of stars and their interactions with surrounding planetary systems. But how do magnetic fields act as cosmic brakes? And what implications does this phenomenon have for our understanding of stars and their worlds? To understand magnetic braking, it's essential to delve into the relationship between a star's magnetic field and its stellar wind. A stellar wind is a stream of charged particles, primarily protons and electrons, continuously emitted from a star's surface. The sun's solar wind, for example, flows outward at speeds of hundreds of kilometers per second, carrying with it the star's magnetic field. This outward flow of plasma and magnetic energy creates a coupling between the star's rotation and its wind, enabling the star to lose angular momentum over time. The process begins with the magnetic field lines anchored in the star's surface. As the star rotates, these field lines twist and stretch outward, interacting with the charged particles in the stellar wind. The particles are guided by the magnetic field, spiraling along its lines and carrying angular momentum away from the star. Over time, this loss of angular momentum causes the star's rotation to slow down, much like a spinning figure skater extending their arms. Magnetic braking is most effective in stars with strong magnetic fields and active stellar winds. Young, low-mass stars, such as those in the early stages of their lives, exhibit intense magnetic activity, with frequent flares and powerful winds. These stars lose angular momentum at a rapid rate, transitioning from rapid rotation to a more sedate pace as they age. The Sun, for example, likely rotated much faster in its youth, but has gradually slowed to its current rate of about one rotation every 27 days. This slowdown has profound effects on the star's behavior and environment. A slower rotation leads to a decrease in magnetic activity, as the dynamo mechanism that generates the magnetic field becomes less efficient. This reduction in activity is reflected in the number and intensity of stellar flares, sunspots, and coronal mass ejections, which all decline as the star ages. For planets orbiting these stars, this means a more stable and less hazardous environment over time, which could be beneficial for the development of life. Magnetic braking also plays a crucial role in the evolution of planetary systems. As stars shed angular momentum, their gravitational influence on nearby planets changes, altering the dynamics of their orbits. For example, planets in close orbits may experience tidal interactions with their host stars, leading to orbital decay or migration. These processes can reshape the architecture of planetary systems, affecting everything from the spacing of planets to their potential habitability. In binary star systems, where two stars orbit each other, magnetic braking can drive dramatic changes in the star's interactions. For instance, in close binary systems, magnetic braking can cause one star to transfer angular momentum to its companion, altering their orbital period and leading to phenomena like mass transfer or the formation of compact objects such as white dwarfs or neutron stars. The study of magnetic braking extends beyond individual stars to broader astrophysical contexts. By measuring the rotational speeds of stars at different stages of their lives, astronomers can reconstruct their rotational histories and infer the efficiency of magnetic braking over time. This information helps refine models of stellar evolution and provides insights into the long-term stability of planetary systems. One of the most exciting applications of magnetic braking research is its use in understanding exoplanetary systems. The rotational slowdown of a star affects the intensity and frequency of its stellar activity, which in turn influences the atmospheres of orbiting planets. For example, young, rapidly rotating stars emit high levels of ultraviolet and X-ray radiation, which can erode planetary atmospheres and strip away water and other volatiles. As the star ages and its rotation slows, these harmful effects diminish, creating a more hospitable environment for potential life. Despite its importance, magnetic braking is not uniform across all stars. Massive stars, for instance, lose much of their angular momentum through mechanisms other than magnetic braking, such as powerful stellar winds driven by radiation. Conversely, low-mass stars, particularly M dwarfs, exhibit extremely efficient magnetic braking due to their strong magnetic fields and intense winds. These differences highlight the diverse ways in which stars evolve and interact with their surroundings. Recent advances in technology are providing new insights into magnetic braking. Space-based observatories like NASA's Kepler and TESS missions have measured the rotational periods of thousands of stars, enabling astronomers to study the relationship between rotation, age, and magnetic activity. Meanwhile, ground-based spectroscopic surveys are revealing the magnetic properties of stars in unprecedented detail, shedding light on the processes that drive angular momentum loss. Magnetic braking is also a focus of theoretical research, with computer simulations playing a key role in understanding the intricate dynamics of stellar magnetospheres and winds. These models, combined with observational data, are helping scientists uncover the physical mechanisms behind magnetic braking and refine their predictions of stellar and planetary evolution. The phenomenon of magnetic braking illustrates the profound interconnectedness of stars and their environments. It shapes the life cycles of stars, influences the architecture of planetary systems, and provides a framework for understanding the habitability of worlds beyond our own. As our knowledge of magnetic braking deepens, it brings us closer to unraveling the mysteries of stellar evolution and the cosmic forces that govern the universe. Interstellar magnetism. The interstellar medium, ISM, the vast expanse of gas, dust, and plasma that fills the space between stars, is far from empty. Threaded through this diffuse material are magnetic fields that shape the ISM structure, dynamics, and evolution. These magnetic fields are invisible but influential, playing a critical role in processes ranging from the formation of stars to the propagation of cosmic rays. Interstellar magnetism, though subtle, is a fundamental force sculpting the cosmos. At first glance, the magnetic fields in the ISM might seem weak, with strengths typically measured in microgauss, 1,000,000 times weaker than a typical refrigerator magnet. However, their influence is profound due to the vast scales over which they operate. These fields extend across light years, threading through molecular clouds, regions of star formation, and even the spaces between galaxies. Their effects are often observed indirectly, through the behavior of the material they interact with. One of the primary roles of interstellar magnetic fields is regulating the collapse of molecular clouds, the dense regions of gas and dust where stars are born. Gravity pulls the material in these clouds inward, driving the formation of protostars. However, magnetic fields thread through the clouds, resisting this collapse by exerting magnetic pressure and tension. This interplay between gravity and magnetism determines the rate and efficiency of star formation, influencing the mass and distribution of the resulting stars. Magnetic fields also guide the flow of gas within the ISM. Observations of polarized light, caused by the alignment of dust grains with magnetic fields, reveal that gas often moves along these magnetic lines. This alignment creates filamentary structures within molecular clouds, where material flows into dense regions to fuel star formation. These filaments, visible in stunning detail in images from telescopes like Herschel, illustrate how magnetic fields shape the ISM's morphology. In addition to guiding gas, magnetic fields influence the behavior of cosmic rays as they travel through the ISM. These high-energy particles are deflected by magnetic fields, their paths bend into spirals and loops. This interaction creates a diffuse glow of radio waves, a signature of cosmic ray, electrons spiraling along magnetic field lines. By studying this radio emission, astronomers can map the structure of the magnetic fields and understand how cosmic rays propagate across the galaxy. Interstellar magnetic fields are not static. They evolve over time, shaped by the dynamics of the ISM. Turbulence, driven by processes like supernova explosions and stellar winds, interacts with magnetic fields, amplifying and distorting them. This turbulent magnetism creates a complex web of forces that influence the ISM's structure and dynamics on scales ranging from individual clouds to entire galaxies. The origin of interstellar magnetic fields remains a topic of intense study. Some theories suggest that these fields are primordial, dating back to the early universe. Tiny magnetic fields generated during the Big Bang could have been amplified over billions of years through processes like the dynamo effect, where the motion of ionized gas stretches and twists magnetic field lines. Alternatively, magnetic fields may arise from localized processes, such as the motion of charged particles in turbulent regions of the ISM. Advances in observational technology are providing new insights into interstellar magnetism. Instruments like the Planck satellite have mapped the polarized emission from dust in the Milky Way, revealing the intricate structure of its magnetic field. Radio telescopes, including the Very Large Array, VLA, and the upcoming Square Kilometer Array, SK, are enabling high-resolution studies of magnetic fields in distant galaxies and the ISM. Interstellar magnetic fields also interact with larger cosmic structures, such as the spiral arms of galaxies. These arms are sites of intense star formation and are threaded with magnetic fields that align with their curves. The alignment suggests that magnetic fields play a role in shaping the arms themselves, guiding the flow of gas and dust that fuels star formation. In the spaces between galaxies, intergalactic magnetic fields extend even farther, connecting galaxy clusters and influencing the large-scale structure of the universe. These fields, though weaker than those in the ISM, provide a critical link between the magnetic environments of individual galaxies and the cosmic web. Observing these vast magnetic structures offers clues about the universe's earliest moments and the processes that shaped its evolution. Magnetism in the ISM also provides a natural laboratory for studying fundamental physics. The interaction of magnetic fields with plasma, the dominant state of matter in the ISM, leads to phenomena like magnetic reconnection and the generation of turbulence. These processes, which occur on scales ranging from the microscopic to the galactic, offer insights into the behavior of magnetic fields in extreme conditions. The study of interstellar magnetism is still a relatively young field, but it is rapidly advancing thanks to new observational and theoretical tools. High-resolution simulations of the ISM are helping scientists model the interaction of magnetic fields with gas, dust, and cosmic rays, while new telescopes are capturing detailed images of magnetic structures in the Milky Way and beyond. Understanding interstellar magnetism is not just about mapping fields. It is about uncovering the forces that shape the cosmos. From the birth of stars to the distribution of matter across galaxies, magnetic fields are a key player in the universe's story. As scientists continue to explore this hidden force, they are piecing together a picture of the ISM that reveals the profound interconnectedness of matter, energy, and magnetism on a cosmic scale. Magnetism on a quantum scale. At the heart of the universe's grand cosmic dance lies an intricate interplay of forces and particles, and magnetism is no exception. While magnetic fields govern phenomena on massive scales, from galactic structures to stellar births, their roots are deeply embedded in the realm of quantum mechanics. Magnetism on a quantum scale reveals the fundamental processes that underpin this ubiquitous force, shedding light on how it arises, operates, and influences matter at its most basic level. Magnetism begins with the movement of charged particles, particularly electrons. Each electron carries an intrinsic property known as spin, a quantum mechanical phenomenon that creates a tiny magnetic field. This spin, combined with the electron's orbital motion around an atomic nucleus, gives rise to magnetism at the atomic level. In most materials, the magnetic moments of individual atoms cancel each other out, rendering the material non-magnetic. However, in certain materials like iron, cobalt, and nickel, these magnetic moments align, producing the strong macroscopic fields we recognize as magnetism. On a quantum scale, magnetism is governed by the exchange interaction, a quantum mechanical effect that causes the magnetic moments of neighboring atoms to align in the same or opposite directions. This alignment depends on the electronic structure of the material and the distances between atoms, leading to phenomena such as ferromagnetism, antiferromagnetism, and ferromagnetism. These behaviors are the foundation of magnetic materials and their applications, from compasses to data storage devices. The quantum origins of magnetism also manifest in superconductivity, a state in which certain materials conduct electricity without resistance when cooled below a critical temperature. In superconductors, magnetic fields interact with the quantum mechanical wave function of electrons, leading to effects like the Meissner effect, where magnetic fields are expelled from the material. This interplay between magnetism and quantum mechanics has profound implications for technology, enabling applications like magnetic levitation and ultra-sensitive magnetometers. One of the most intriguing aspects of quantum magnetism is the emergence of magnetic phenomena in low-dimensional systems. In one-dimensional chains of atoms, two-dimensional sheets, and other nanoscale structures, magnetic behaviors can differ dramatically from those observed in bulk materials. These systems provide a playground for studying exotic quantum states, such as spin liquids, where magnetic moments fluctuate rather than aligning, even at absolute zero. Spin liquids are of particular interest because they defy conventional magnetic order, offering potential pathways to quantum computing and other advanced technologies. Quantum magnetism is also central to understanding the behavior of strongly correlated electron systems, where the interactions between electrons dominate over their individual motions. In these systems, magnetism often competes with other quantum effects, leading to phenomena like high-temperature superconductivity and the formation of magnetic vortices. These effects challenge our understanding of quantum mechanics and open new avenues for exploring the interplay between magnetism, electron interactions, and quantum states. The study of magnetism at the quantum level has applications far beyond materials science. In astrophysics, the quantum origins of magnetism help explain the behavior of matter under extreme conditions, such as the interiors of neutron stars and the environments around black holes. These environments push the limits of magnetic fields, creating conditions where quantum mechanics and general relativity intersect. In particle physics, magnetism plays a role in fundamental interactions. For example, the magnetic dipole moments of particles like protons and neutrons are key to understanding the forces that hold atomic nuclei together. These moments also provide clues about physics beyond the standard model, as deviations from predicted values could indicate the presence of new particles or forces. Technological advances are enabling unprecedented exploration of magnetism on a quantum scale. Techniques like neutron scattering and X-ray magnetic circular dichroism allows scientists to probe the magnetic properties of materials at the atomic level. Meanwhile, quantum computers and simulators are providing new tools for modeling complex magnetic systems, offering insights into phenomena that were previously beyond reach. As our understanding of quantum magnetism deepens, it continues to reveal connections between the micro and macro scales, linking the behavior of individual particles to the grand magnetic structures that shape the universe. From the alignment of electron spins to the fields that thread through galaxies, magnetism exemplifies the profound interconnectedness of nature. Magnetism on a quantum scale is not just a scientific curiosity. It is a cornerstone of modern physics and technology. Its principles underpin the devices we use every day, from smartphones to MRI machines, and its mysteries drive the development of next-generation technologies, including quantum computing and advanced materials. As researchers continue to explore this quantum frontier, they are not only uncovering the roots of a fundamental force, but also paving the way for a future shaped by the quantum world. Earth's magnetic anomalies. Earth's magnetic field is a cornerstone of the planet's ability to support life, shielding the surface from harmful cosmic radiation and solar wind particles. But this magnetic shield is far from uniform or constant. Scattered across the globe are magnetic anomalies, regions where the magnetic field deviates significantly from the expected pattern. These irregularities hold clues about Earth's dynamic core, the processes shaping the planet's interior, and the field's future behavior. What causes these anomalies? And what do they reveal about the ever-changing nature of Earth's magnetism? At the heart of Earth's magnetic field lies the geodynamo, a process driven by the movement of molten iron and nickel in the planet's outer core. This churning motion generates electric currents, which in turn produce the magnetic field. However, this process is not perfectly symmetrical. Variations in temperature, pressure, and composition within the core create localized differences in the field's strength and direction, leading to magnetic anomalies. One of the most prominent examples of a magnetic anomaly is the South Atlantic Anomaly, SA, a region where Earth's magnetic field is significantly weaker than average. Located over parts of South America, the Southern Atlantic Ocean, and Africa, the SAA exposes satellites and spacecraft to higher levels of radiation, posing challenges for navigation and communication systems. Scientists believe the anomaly is linked to irregularities in the outer core, where reversed magnetic field lines weaken the overall field strength in this region. Magnetic anomalies are not limited to the surface. Beneath the Earth's crust, variations in the magnetic properties of rocks create localized distortions in the field. These anomalies are particularly evident in areas with large deposits of iron-rich minerals or volcanic rocks, which retain magnetic signatures from the time they formed. By studying these anomalies, geologists can uncover details about the planet's tectonic history, including the movement of continents and the formation of mountain ranges. Earth's magnetic field is also subject to reversals, where the magnetic north and south poles switch places. These geomagnetic reversals occur irregularly, roughly every few 100,000 years, and are recorded in the magnetic signatures of rocks. During a reversal, the field's strength weakens, and multiple magnetic poles may emerge, creating complex patterns of anomalies. The last major reversal, the Bruns-Machiyama reversal, occurred about 780,000 years ago, but evidence suggests we may be due for another in the distant future. In addition to global reversals, the magnetic poles themselves are constantly shifting. The magnetic North Pole, for example, has been moving at an accelerating rate from Canada towards Siberia. This movement, driven by changes in the core's flow, alters the distribution of magnetic anomalies and has implications for navigation systems that rely on magnetic compasses. Magnetic anomalies are not unique to Earth. They are observed on other planets and moons as well. For example, Mars exhibits localized magnetic fields in its crust, remnants of an ancient global magnetic field that has long since disappeared. Studying these anomalies provides insights into the early history of Mars and its potential for habitability. Similarly, anomalies on the Moon, caused by magnetized crustal materials, offer clues about its geological history and the impact processes that shaped its surface. Detecting and mapping magnetic anomalies require advanced technology and techniques. Satellites like the European Space Agency's swarm mission measure variations in Earth's magnetic field with high precision, providing detailed maps of anomalies and their evolution over time. On the ground, magnetometers and airborne surveys allow scientists to study anomalies in greater detail, linking them to geological features and processes. Magnetic anomalies also have practical applications. In resource exploration, anomalies can indicate the presence of valuable minerals, oil, and gas deposits. They are also used in archaeology to locate buried structures and artifacts, as well as in navigation systems for correcting deviations caused by local magnetic variations. Despite their importance, many questions about Earth's magnetic anomalies remain unanswered. What drives the formation and evolution of anomalies like the South Atlantic anomaly? How do changes in the core influence the field on short and long timescales? And what can these anomalies tell us about the future stability of Earth's magnetic field? The study of magnetic anomalies is a window into the dynamic processes shaping our planet. They reveal the complexity of Earth's interior, the interactions between its layers, and the connections between its magnetic field and surface features. As scientists continue to explore these anomalies, they are uncovering a deeper understanding of the forces that sustain our planet's magnetic shield and its role in protecting and shaping life on Earth. Jupiter, the magnetic king. Jupiter, the largest planet in our solar system, is not just a king in size. It reigns supreme when it comes to magnetic fields. Its magnetosphere, the region dominated by its magnetic influence, is the largest structure of its kind in the solar system, dwarfing the planet itself. Stretching millions of kilometers into space, Jupiter's magnetic field shapes the environment around it, governs interactions with its moons, and generates powerful phenomena that offer a glimpse into the planet's interior. But what makes Jupiter's magnetic field so extraordinary? And what does it reveal about the planet and its cosmic domain? Jupiter's magnetic field is generated by the dynamo effect, similar to Earth's, but on a far grander scale. Deep within Jupiter lies a layer of metallic hydrogen, a state of hydrogen achieved under immense pressure and temperature. In this metallic state, hydrogen conducts electricity, and the planet's rapid rotation, completing a day in just under 10 hours, creates electric currents that generate a powerful magnetic field. This combination of material and rotation produces a magnetic field approximately 20,000 times stronger than Earth's. The scale of Jupiter's magnetosphere is staggering. If it were visible from Earth, it would appear several times larger than the full moon in the night sky. The magnetosphere stretches about 3 million kilometers toward the Sun and extends well beyond Saturn's orbit on the side opposite the Sun. Within this vast region, charged particles from the solar wind and Jupiter's own volcanic moon, Io, interact with the magnetic field, creating a dynamic and complex environment. Io, the most volcanically active body in the solar system, plays a crucial role in shaping Jupiter's magnetosphere. Its eruptions release vast quantities of sulfur dioxide gas, which becomes ionized and forms a plasma torus, a ring of charged particles that orbits Jupiter. This plasma interacts with Jupiter's magnetic field, generating intense radiation belts and contributing to the planet's auroras. Io's unique relationship with Jupiter's magnetosphere creates electromagnetic waves that travel along magnetic field lines, producing bursts of radio emissions detectable from Earth. Jupiter's auroras, the brightest in the solar system, are among the most striking manifestations of its magnetic power. Unlike Earth's auroras, which are primarily caused by interactions between the solar wind and the magnetosphere, Jupiter's auroras are driven by its rapid rotation and the interaction with its moons, particularly Io. These auroras emit light across a wide range of wavelengths, from ultraviolet to infrared, and provide insights into the planet's magnetic dynamics and its interaction with the solar wind. The interaction between Jupiter's magnetosphere and its other moons also creates fascinating effects. For example, Europa, Ganymede, and Callisto experience variations in their magnetic environments as they orbit within Jupiter's field. Ganymede, the largest moon in the solar system, even has its own magnetic field, making it the only moon known to possess a magnetosphere. The interaction between Ganymede's magnetic field and Jupiter's creates a complex, layered magnetic environment that scientists are still working to understand. Jupiter's magnetosphere also has a profound impact on its surrounding space. The planet's powerful magnetic field captures high-energy particles, creating intense radiation belts that pose significant challenges for spacecraft. These radiation belts are so strong that they can damage or destroy unshielded electronics, making missions to Jupiter and its moons a technical challenge. Despite these challenges, missions like NASA's Juno spacecraft have provided unprecedented insights into Jupiter's magnetic field. Juno, which orbits close to the planet, carries instruments designed to map the magnetic field in detail. Its observations have revealed that Jupiter's magnetic field is not uniform. It exhibits surprising asymmetries, with regions of unexpectedly strong or weak magnetism. These findings suggest that the processes occurring in Jupiter's interior are more complex than previously thought. Jupiter's magnetic influence extends far beyond its immediate surroundings. The interaction between its magnetosphere and the solar wind creates a bow shock, a region where the solar wind slows and diverts around the planet. This bow shock and the structures it creates influence the flow of charged particles in the outer solar system, connecting Jupiter's magnetic domain to the broader heliosphere. The study of Jupiter's magnetic field is not just about understanding the planet itself. It provides broader insights into planetary magnetism and the dynamics of gas giants. By comparing Jupiter's magnetic field to those of other planets, such as Saturn and Uranus, scientists can identify commonalities and differences that shed light on the processes driving magnetic fields across the solar system. Jupiter's magnetic power also has implications for the search for life beyond Earth. Its strong radiation belts pose challenges for missions to its moons, particularly Europa, which is a prime candidate for hosting subsurface life. Understanding Jupiter's magnetosphere is essential for designing spacecraft that can explore these environments while minimizing exposure to harmful radiation. As scientists continue to study Jupiter's magnetic field, they are uncovering the intricate connections between the planet's interior, its moons, and its space environment. Jupiter stands as a testament to the complexity and grandeur of planetary magnetism, a cosmic powerhouse that dominates the solar system's magnetic landscape and provides endless opportunities for exploration and discovery. Exploring magnetism on Mars. Mars, the red planet, is a world of contrasts. Once home to flowing rivers and vast lakes, now a cold desert with a thin atmosphere. Central to Mars's transformation is its magnetic history, a story written in the rocks and preserved in the planet's crust. Unlike Earth, Mars no longer has a global magnetic field, a loss that has profoundly shaped its surface, climate, and potential habitability. What happened to Mars's magnetic field, and what can its remnants tell us about the planet's past? Billions of years ago, Mars had a dynamo-driven magnetic field similar to Earth's. This global magnetic field likely shielded its surface from the solar wind, preserving a thick atmosphere that supported liquid water. Evidence for this ancient magnetic field comes from studies of the planet's crust. Certain regions of Mars's crust exhibit strong, localized magnetism, remnants of a time when the planet's core was active and generating a global field. These magnetic signatures are fossilized in the rocks, providing a snapshot of Mars's magnetic past. The cessation of Mars's dynamo is one of the most significant events in the planet's history. Scientists believe that the dynamo shut down around 4 billion years ago, possibly due to the cooling of the planet's core or changes in its internal dynamics. Without a global magnetic field, Mars became vulnerable to the solar wind, which gradually stripped away much of its atmosphere. This loss of atmosphere likely drove the planet's transition from a warm, wet world to the cold, arid one we see today. Mars's magnetic crustal anomalies are most prominent in the southern hemisphere, where large swaths of the terrain exhibit strong magnetic signatures. These anomalies are thought to have formed during the early stages of the planet's history, when the dynamo was still active. The distribution and intensity of these anomalies provide clues about the structure of Mars's crust and the dynamics of its ancient magnetic field. One of the most intriguing aspects of Mars's magnetic anomalies is their potential connection to the planet's early tectonic activity. The patterns of magnetization in the crust suggest that Mars may have experienced plate tectonics during its early history, similar to the processes that shape Earth's surface today. If true, this would have significant implications for our understanding of Mars's geological evolution and its potential for supporting life. The absence of a global magnetic field has left Mars exposed to the full force of the solar wind. This interaction creates an induced magnetosphere, a weak magnetic barrier generated by the interaction between the solar wind and the ionized layer of Mars's atmosphere. Unlike Earth's magnetosphere, which is generated internally, Mars's induced magnetosphere is shaped entirely by external forces. This makes it a valuable natural laboratory for studying the interactions between solar wind and unprotected planetary atmospheres. Mars's magnetic history also influences the behavior of its atmosphere today. The loss of a global magnetic field allowed the solar wind to strip away much of Mars's atmosphere, but the process is ongoing. Observations from missions like NASA's MAVEN, Mars Atmosphere, and Volatile Evolution spacecraft reveal that the solar wind continues to erode the Martian atmosphere, particularly during solar storms when the flow of charged particles intensifies. Despite the challenges posed by the loss of a global magnetic field, Mars remains a prime candidate for studying the potential for life beyond Earth. Its crustal anomalies could provide localized protection from cosmic and solar radiation, creating pockets where life might have survived or persisted. These regions of strong magnetism may have shielded subsurface environments, preserving conditions favorable for microbial life. The study of Mars's magnetic anomalies is also critical for future exploration. Human missions to Mars will need to account for the planet's lack of a global magnetic shield, as radiation poses a significant risk to astronauts and equipment. Understanding the distribution of crustal magnetic fields could help identify regions that offer natural protection, making them ideal sites for habitats or scientific research. Technological advancements are enabling new approaches to studying Mars's magnetism. Orbital missions equipped with magnetometers, such as ESA's Mars Express and NASA's MAVEN, have mapped the planet's magnetic anomalies in detail, providing insights into their origins and distribution. Future missions, including surface-based investigations, could explore these anomalies more closely, analyzing the magnetic properties of rocks and linking them to the planet's geological history. Mars's magnetic story is not just about its past. It also holds lessons for understanding planetary magnetism across the solar system and beyond. By comparing Mars to other planets, such as Earth and Venus, scientists can identify the factors that sustain or extinguish global magnetic fields. These comparisons are essential for assessing the habitability of exoplanets, where magnetic fields play a key role in protecting atmospheres and enabling life. As we continue to explore Mars, its magnetic field serves as a reminder of the forces that shape planets and their environments. From the ancient dynamo that protected a young, water-rich world to the crustal anomalies that preserve its memory, Mars's magnetism offers a window into the planet's history, evolution, and potential for life. Unlocking these magnetic mysteries brings us closer to understanding not only the red planet, but also the broader story of planetary evolution in the universe. Magnetic forces in cosmic collisions. In the vast, ever-changing tapestry of the cosmos, collisions between galaxies, stars, and clouds of gas are among the most dynamic and transformative events. While gravity is the primary driver of these interactions, magnetic fields play a critical, albeit less visible, role in shaping the outcomes of such collisions. From guiding the flow of matter to amplifying turbulence, magnetic forces add complexity to these cosmic encounters, revealing the intricate interplay between unseen forces and visible structures. How do magnetic fields influence these high-energy events, and what can they teach us about the universe? When galaxies collide, as they often do in the densely packed clusters of the universe, the magnetic fields of each galaxy are drawn into the chaotic mix. These fields, though relatively weak, become stretched, tangled, and compressed as the galaxies merge. The intense turbulence generated by the collision amplifies the magnetic fields, a process known as a dynamo effect. This amplification can increase the strength of magnetic fields by several orders of magnitude, creating localized regions of intense magnetism. One of the most striking consequences of galactic collisions is the formation of large-scale shockwaves, where the colliding gas clouds compress and heat up to millions of degrees. Magnetic fields are critical in shaping these shockwaves, guiding the motion of charged particles and influencing the structure of the resulting plasma. These magnetic shock waves are not just markers of the collision, but also sources of high-energy phenomena, such as cosmic rays and synchrotron radiation, which emit light across a wide range of wavelengths. The role of magnetic fields extends to star formation within colliding galaxies. As the galaxies merge, the compression of gas clouds triggers a burst of star formation, often producing thousands of new stars in a relatively short period. Magnetic fields thread through these clouds, regulating their collapse and influencing the size, distribution, and properties of the resulting stars. Observations of starburst galaxies, where such intense star formation occurs, reveal that their magnetic fields are often stronger and more chaotic than those of isolated galaxies, a testament to the dynamic interplay between magnetism and gravity. Magnetic fields also play a role in the behavior of supermassive black holes at the centers of colliding galaxies. As gas and dust are funneled toward the black holes during the merger, the material forms accretion disks threaded with magnetic fields. These fields can drive powerful jets of plasma that shoot out from the black holes at near-light speeds, shaping the environment on galactic scales. The interaction between the magnetic fields of merging galaxies and the jets from their central black holes adds another layer of complexity to these colossal events. Beyond galaxies, magnetic forces influence collisions on smaller scales, such as between massive molecular clouds. These clouds, the nurseries of stars, are often magnetized, and their interactions create regions of intense turbulence and compression. Magnetic fields in these environments help shape the resulting structures, from dense filaments to the stars themselves. By resisting or guiding the collapse of material, magnetism adds an additional force that interacts with gravity and thermal pressure, determining the outcome of these collisions. On even larger scales, the collision of galaxy clusters, the largest gravitationally bound structures in the universe, provides a spectacular stage for magnetic forces. When clusters merge, their vast magnetic fields interact, creating shockwaves that propagate across millions of light years. These shockwaves amplify the magnetic fields and accelerate particles to high energies, producing giant radio halos and relics, features that glow brightly in radio wavelengths and are directly tied to magnetic phenomena. Observations of these relics, such as those seen in the Coma cluster, offer clues about the magnetic fields pervading these cosmic structures. The study of magnetic forces in cosmic collisions is a rapidly evolving field, driven by advancements in observational technology. Radio telescopes like the Very Large Array, VLA, and the Low Frequency Array, LOFAR, are providing detailed maps of magnetic fields in colliding galaxies and clusters, revealing their structure and evolution. Meanwhile, X-ray observatories like Chandra and XMM Newton are capturing the hot, magnetized plasma produced in these events, offering complementary views of the magnetic dynamics at play. Theoretical simulations are also shedding light on how magnetic fields behave during cosmic collisions. By modeling the interaction of magnetic fields with gas, stars, and dark matter, scientists can recreate the conditions of real-world mergers and explore the physical processes that shape their outcomes. These simulations are helping to bridge the gap between observation and theory, providing a deeper understanding of the role of magnetism in the universe. Magnetic forces in cosmic collisions are not just a scientific curiosity. They are a key to understanding the fundamental workings of the universe. By influencing the flow of matter, the formation of stars, and the behavior of black holes, magnetic fields shape the cosmos in profound ways. As scientists continue to study these forces, they are uncovering the hidden structures and dynamics that govern the universe, revealing the intricate and interconnected nature of the forces that define our cosmic home. Magnetic fields and the Big Bang. Magnetism, a force that permeates the cosmos, did not emerge haphazardly. Its origins can be traced back to the very birth of the universe, the Big Bang. Though magnetic fields today govern processes ranging from the formation of stars to the structure of galaxies, their primordial beginnings remain one of the most compelling mysteries in astrophysics. How did the universe's first magnetic fields form, and how have they evolved over billions of years to shape the cosmos we observe today? To understand the origins of magnetic fields, we must begin with the conditions shortly after the Big Bang. Approximately 13.8 billion years ago, the universe was a hot, dense plasma of particles and radiation. In this primordial state, protons, electrons, and photons moved in a highly energetic soup, governed by the interplay of fundamental forces. As the universe expanded and cooled, particles began to combine into neutral atoms during a period known as recombination, roughly 380,000 years after the Big Bang. Before recombination, the charged particles in the primordial plasma interacted with electromagnetic fields. Turbulence in this plasma, driven by density fluctuations, may have generated tiny magnetic fields through processes like plasma instabilities or vorticity. These weak seed magnetic fields, measured in strengths as low as 10^2 Gauss, would have been the precursors to the cosmic magnetic fields we observe today. Another theory suggests that magnetic fields could have arisen even earlier, during cosmic inflation, a brief but exponential expansion of the universe that occurred a fraction of a second after the Big Bang. During this phase, quantum fluctuations in the electromagnetic field could have been stretched across cosmic scales, creating the seeds of magnetic fields. If true, these primordial fields would carry information about the physics of inflation and the early universe. Regardless of their exact origin, these primordial magnetic fields would have been amplified over time by the dynamo effect, a process in which the motion of conductive fluids or plasma strengthens magnetic fields. As the universe evolved, the collapse of gas into stars, galaxies, and clusters provided the conditions for such amplification. Magnetic fields grew from their weak initial states into the coherent structures that now thread through galaxies and span intergalactic space. Evidence for these primordial magnetic fields comes from a variety of sources. One of the most promising avenues is the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. If primordial magnetic fields existed, they would have influenced the polarization of the CMB, leaving subtle imprints that scientists can analyze. Instruments like the Planck satellite and upcoming missions aim to detect these signatures, offering a glimpse into the universe's magnetic infancy. Magnetic fields also leave their mark on the large-scale structure of the universe. As galaxies and clusters formed, magnetic fields influenced the motion of gas and plasma, guiding the formation of filaments and voids in the cosmic web. Observations of magnetic fields in galaxy clusters, particularly the diffuse radio emissions from relativistic particles spiraling along magnetic field lines, provide indirect evidence of these ancient fields. The existence of intergalactic magnetic fields, detected through their effects on cosmic rays and the polarization of light from distant quasars, further supports the idea of a primordial origin. These fields, though weak, are remarkably uniform across vast distances, suggesting they were seeded early in the universe's history and have persisted for billions of years. Studying primordial magnetic fields has profound implications for our understanding of fundamental physics. By probing these fields, scientists can test theories of cosmic inflation, particle physics, and the unification of forces. For example, certain models of inflation predict specific patterns in the strength and distribution of magnetic fields, which can be compared with observations. Similarly, the behavior of magnetic fields in the early universe may provide clues about the nature of dark matter and dark energy. Despite their importance, primordial magnetic fields remain elusive. Their weak strength and the challenges of distinguishing them from magnetic fields generated by later astrophysical processes make them difficult to detect. However, advancements in technology and observational techniques are bringing us closer to unraveling their mysteries. Future instruments, such as the Square Kilometre Array, SKA, and next-generation CMB observatories, will have the sensitivity to detect the faint imprints of primordial magnetic fields. These observations, combined with sophisticated simulations, will help reconstruct the evolution of magnetic fields from the Big Bang to the present day. Understanding the origins of magnetic fields is not just about tracing a single cosmic force. It is about piecing together the story of the universe's earliest moments. From the quantum fluctuations of inflation to the formation of galaxies and beyond, magnetic fields are woven into the fabric of cosmic history. As scientists continue to explore this frontier, they are uncovering a deeper understanding of how the universe's most fundamental forces have shaped its evolution. Magnetic stars and pulsars. Among the celestial wonders that populate our universe, certain stars exhibit magnetic fields of extraordinary strength, influencing their behavior and interactions with their surroundings. From magnetic stars that confound our understanding of stellar physics to pulsars, nature's most precise cosmic clocks, these objects reveal the profound impact of magnetism on stellar evolution and dynamics. What makes these stars so magnetic, and what secrets do pulsars hold about the universe's extreme environments? Magnetic stars are a diverse group, encompassing various types of stars with unusually strong magnetic fields. Among the most well-known are AP/BP stars, a subset of chemically peculiar stars whose magnetic fields range from hundreds to tens of thousands of Gauss, far exceeding the Sun's relatively modest magnetic field. These fields influence the distribution of elements on their surfaces, creating striking spectral patterns that set them apart from other stars. The origin of magnetic fields in these stars is still a subject of debate. Some theories suggest that the fields are fossil remnants from the molecular clouds where the stars formed, preserved during the star's collapse. Others propose that these fields are generated by a dynamo mechanism within the stars, driven by the motion of plasma in their interiors. Understanding the source of these magnetic fields could provide insights into the conditions of star formation and the processes that sustain stellar magnetism. Magnetic stars also include magnetars, the highly magnetized remnants of massive stars that exploded as supernovae. These neutron stars possess magnetic fields up to 1,000 trillion Gauss, the strongest in the known universe. Magnetars are known for their extreme behavior, including violent outbursts of X-rays and gamma rays caused by the sudden rearrangement of their magnetic fields. These outbursts, which release as much energy in seconds as the Sun does in a year, highlight the immense power of magnetic forces in these compact objects. Among the magnetic stars, pulsars hold a special place in astrophysics. Pulsars are rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky like lighthouse beacons, creating regular pulses of light and radio waves as the star rotates. The precision of these pulses, which can be accurate to millionths of a second, makes pulsars some of the most reliable natural clocks in the universe. The magnetic fields of pulsars are central to their behavior. As the neutron star spins, its intense magnetic field generates electric fields that accelerate particles to nearly the speed of light. These particles produce radiation that escapes along the magnetic field lines, creating the beams observed as pulses. The interaction between the star's rotation and its magnetic field also causes pulsars to gradually lose energy, leading to a slow but measurable decrease in their rotation rate over time. Pulsars come in various types, each with unique characteristics. Millisecond pulsars, for instance, are neutron stars that have been spun up to incredibly high rotation rates by accreting material from a companion star. These objects can rotate hundreds of times per second, their extreme speeds creating magnetic fields that drive some of the most energetic processes in the universe. One of the most fascinating applications of pulsars is their use in testing the fundamental laws of physics. Their precise timing makes them ideal for studying general relativity, as the motion of pulsars in binary systems allows scientists to measure the warping of space-time caused by massive objects. Pulsars also serve as cosmic detectors for gravitational waves, the ripples in space-time caused by the collision of massive celestial bodies. By monitoring the timing of pulsar signals across the galaxy, astronomers can detect subtle distortions in space-time caused by passing gravitational waves. The study of pulsars has also revealed extreme environments that push the limits of our understanding of matter and magnetism. The interiors of neutron stars, for instance, contain matter at densities that exceed those of atomic nuclei, creating conditions where exotic states of matter, such as quark-gluon plasma, may exist. The magnetic fields of pulsars influence the behavior of this matter, offering a window into physics that cannot be replicated in laboratories on Earth. Despite decades of study, pulsars and magnetic stars continue to surprise and challenge astronomers. For example, the discovery of pulsars with irregular, intermittent pulses, known as nulling pulsars, raises questions about the stability of their magnetic fields and the mechanisms driving their emissions. Similarly, the observation of magnetars with radio pulses blurs the line between these highly magnetized objects and more conventional pulsars, suggesting a continuum of magnetic behavior among neutron stars. Technological advancements are expanding our ability to study these magnetic wonders. Radio telescopes like the Square Kilometer Array, SKA, and space-based observatories are enabling the detection of more pulsars and the detailed study of their emissions. X-ray and gamma-ray telescopes, such as NASA's NICER and the European Space Agency's Athena, are providing new insights into the high-energy behavior of magnetars and other magnetic stars. Magnetic stars and pulsars are not just objects of scientific interest. They are cosmic laboratories where the laws of physics are tested under the most extreme conditions. Their study is revealing the interplay between magnetism, rotation, and matter on scales that range from the subatomic to the interstellar. As we continue to explore these enigmatic objects, they offer not only answers to long-standing questions, but also glimpses into the fundamental forces that shape the universe. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.